in the units where c is equal to 1. During a TV contact, people on Earth noticed that time runs faster on board. By how much? How come the astronauts become younger than people on Earth? Okay, so this is basically a relativistic Doppler shift problem because we have a TV signal that's blue shifted because it's the Earth here. The spaceship is approaching by 0.995.
Excuse, can you break the chalk?
Okay, but I don't think it's a problem because it's okay.
Or is it because
The quality of the job.
No, that's better. Yes. Okay. So the frequency of the TV signal would be shifted by 1 plus.
Oh, sorry, before equation, can you draw a space-time diagram?
For this, okay. Yeah.
Say for the whole trip, imagine we are at x equal to 0 on Earth.
This is x equal to 0 on Earth.
And then the spaceship goes
And this is the
away and comes back.
Okay, but say that the ship is just coming back.
Yeah, let's imagine that at some point it went away.
Okay.
Because I think it would be useful to have that piece.
I'll be here. Went and then came back. And came back to Earth.
Okay. So now you are looking at the second piece of the tree.
This from here to here, because the problem is concerned about here.
And then we can have some signal that is sent.
Yes, a TV signal that's sent. So it would be blue shifted by the ratio 1 plus v over 1 minus v, which would be 1 plus 0.995 over 1 minus 0.995. That would be 19.97 times. For the TV signal. That's for the first part. The second part says, how come the astronauts become younger than people on Earth? Okay. We observe that the signal is faster due to the Doppler shift, but the people become younger on this shift because their proper time would be less than the time on Earth by a factor of gamma due to the time dilation. Basically, so they don't age due to Doppler effect. They age due to this at the time where they are considered to be at rest.
So imagine this TV contact is continuous. So from the time at which they start the trip until the time they return, we are continuously.
Yes, from here to here.
Yeah. Imagine we are continuously watching the clock.
Okay.
So what would we see? Because if it works slower during the whole trip and you are watching it, then it cannot, at the end of the day, it cannot be, the total time cannot be more. Sorry, the other way around. If we are watching it the whole time and it goes faster the whole time, at the end the full result cannot be shorter.
Yes.
So what would happen if we were watching the
okay, here it
constant?
Would be, okay, for this, because it would be heading away from the Earth, not towards the Earth. So it won't be blue shifted, it would be red shifted. So it will appear that it runs slower than. And
so when it goes away, what we see is that the
from
clock
the TV
works slower. Can you draw some light signals from the spaceship to Earth?
Light signals?
Yeah. So these TV signals that they are sending, we should be able to draw them too.
Okay, from here, we need to send to Earth, so we need to draw lines with slope of 1.
Yeah, the only thing that, the most important thing is the slope of these signals compared to the velocity of the spaceship. So the spaceship is supposed to be sublumina.
Yes, to be 0.995, and for the light it would be 1.
Yeah.
The slope would be 1.
Mm.
So it would be.
Oh, sorry, I thought the spaceship is sending us
the
the
light.
signal.
So
Not
that way.
we are watching them, they are not watching us.
Yes. The spaceship. Okay, so they will. Yes, with this station.
So let me ask you, there is that turning point. There is a signal that is sent at the turning point.
This.
Yeah, so I think one thing to understand qualitatively is whether the signal, when does that signal at the turning point arrives on Earth? Just qualitatively.
When does it arrive on Earth? Okay,
I mean, what I'm asking is whether it arrives before the spaceship arrives to Earth or after.
if it's sent from here,
Yeah.
yes, it arrives before the spaceship.
Okay, so just draw something. Okay, good. So now we have two regions, right?
I broke the chalk already.
Is it one of the good ones? No. So we have two regions, non-overlapping regions, right? So what is the difference between the two regions? This is the redshift part,
Yes.
right? And this is the blue shift part. So during this period, what we see is that the clock is moving slower, and then during this period it works faster. But it works slower for a longer time compared to
the part. So overall, the astronauts will age less because this part is
Longer.
because the clock runs slower for most of the time than it runs faster.
Okay, thank you. Esteban.
Which problem?
Problem 3.
Here. So I have an accelerator spaceship. So I know the equation of motion in terms of
Can you just say what the problem?
Basically, it says,
Imagine some people are watching.
an ideal photon spaceship and transforming field mass to energy of ideal collimated photons with 100% of efficiency goes to the center of the galaxy away from a distance parsec. And back. It starts from rest and finishes at rest. The acceleration and deceleration are equal to a 10 meters square. And the questions are the trip time by Earth and onboard clock. The first part, they are asking me about the time measured on Earth and the time measured on the spaceship. So the proper time of the spaceship.
Okay.
So I know that
We need some pictures first. A diagram.
Yeah, I will. So this is an accelerator moving frame. So I can draw as in rainbow coordinates. So here something like this. Will be the geodesic or the trajectory of the spaceship because it's accelerated. And I have on Earth, I will choose that Earth is not accelerating, so we choose that's our reference frame. And I can say, okay, it will be here. So the equation of motion of accelerator observator.
But don't they leave from the Earth?
Oh, it should be like here. They go.
But don't they start from rest?
Yes, but they will accelerate. So.
But I thought they start from rest on Earth.
Here.
But that's not at rest. Who is Earth? Earth is the straight line, right?
This one.
Okay, so now if I want somebody to be at rest with respect to Earth, what would be the tangent to the world line?
90 degrees.
The tangent to this world line.
Well, I'm saying, imagine someone is at rest with respect to Earth. So there is an observer who has some world line, right? Any observer has a world line. Now imagine an observer who is at rest with respect to Earth at some moment. Then we can ask what is the tangent to that world line.
Well, the way that I solve the problem is that I know how the coordinates in terms of the Earth can be related with the proper time and to the spaceship.
But
so,
say I have something. Say I don't know. Say there is some spaceship that passes by the Earth, so near the Earth, and it moves with some velocity. Can we draw that on this space-time diagram?
Well, I don't know.
Well, there is a spaceship that moves with constant velocity, and at t equal to 0, it is at Earth. So can we draw that?
So it should be tangent to this line, right?
Well, if it has constant velocity, or let's consider this example. So remember we had this Bob or this Charlie example. So there was Bob who was at rest, and then there was Alice who was moving with constant velocity. So what would their word lines look like? Say we are in the Bob's rest frame. So what is the Bob's word line?
Bob is at rest, right?
Bob is at rest, yeah.
Should we keep there this one?
Mm-hmm.
The other should be
Okay.
less than 6.
Uh-huh. So this is someone who moves with constant velocity compared to Bob, and at t equal to 0, they are at the same location.
Mm-hmm. Yeah.
But they are not at rest with respect to each other, right? So at t equal to 0, they have, you can imagine that this line continues to the past.
Mm-hmm. Yeah.
So it's just an observer now Alice is an observer with constant velocity that moves, that passes by Bob.
Mm-hmm.
Okay. Now we
For
want...
the accelerator case, it should be I don't see some. I don't know.
So I'm asking, imagine there is now another observer on the same diagram. Say there is another observer who at t equal to 0 is at the same location as Bob. However, its velocity at t equal to 0 is 0 with respect to Bob.
Yes. Well, I don't feel so good right now. I don't know why. So anyone else can do the exercise because
Okay.
I don't feel so good. So I don't know why.
It's okay. Azim?
I didn't do number 3. Maybe I can do the 4th or the 5th.
Alejandro?
So yeah, but I had thought about it like the same because I thought that for accelerator frames was supposed to be like this, but wait, I mean, which one? This is like the Earth,
This time.
Mm-hmm.
right? So it would be for an observer that is at rest with respect to Earth would be just another line
Uh-huh.
on top of it.
Uh-huh.
So, but then it would be like that. It would be then the
Right.
accelerated motion.
Uh-huh.
So then what I did was pretty much the same, just correlating these actions to the transformation. Since we have...
Sorry, before a question, can we have the diagram for the whole trip? Because it goes somewhere and comes back.
Okay.
So this is correct that when it leaves the Earth, it should look like this. But let's have a bigger diagram that shows the full trip, or maybe a smaller scale, so that we see the whole trip of going to the
So-
center of galaxy and coming back.
And comes back. Oh. But yeah, we go away like this. But if you will stop at some point. Oh no, sorry. Yeah, so it goes like that. So it will go, that I think it's 10 kiloparsecs. But then it will come back to Earth. So yeah, no, sorry, how would you?
Well, it wants to be. So imagine you wanted to go. You imagine you were that astronaut. You wanted to go and you wanted to be at rest when you arrive at the center of the galaxy, right? So at first you turn on your engine, you have positive acceleration as you go. But if you want to be at rest, when you arrive at the center, at some point you should turn around the engine.
Yeah.
So you have to decelerate so that when you arrive at the center, you are at rest. Deceleration is basically almost the same diagram, except that now it
Slope
is.
Yes.
And go back.
And go.
And then you go back here. And see.
Yes.
Yeah.
Okay.
Can I jump to the questions? Or any other questions?
Yeah.
Yeah, okay. So yeah, that would be the force. So then just we have like the distance. Since we have like units, I'm putting C back on the transformation.
So what is when is tau equal to 0 on this diagram?
Tau equal to 0?
Yeah.
Yeah, here again. So, I don't know. Yes, 0. What is sine hyperbolic 0?
Should be -1.
It's -1. Sine hyperbolic 0 is -1.
No.
Zero.
I mean 0. Yes.
That t equals 0 and 2.
But tau equal to 0 should correspond to a point,
Yes.
an event on this diagram. So I guess I'm asking what is that point?
It would be the same t equals 0.
No, because
But the cosh is 1.
Okay.
So there is a -1 there.
Okay.
So this is assuming that the x of the earth is 1.
So, okay, so, sorry, the t will be equal to 0. So something like that. So the x would be minus 1 minus square divided by 8.
Yeah. What is cosine hyperbolic of 0?
I don't know.
One.
It's
One?
1.
Okay. Sorry. Like that. So yeah.
Well, the
But what-
definition.
yeah,
Let's go back to the
Ah,
definition.
cosine.
What is the definition of cosine hyperbolic of x? Okay, it's e to the cosine x is e to the x plus e to the minus x divided by 2. So at 0 it is 1.
Yeah. So
So if we want to take position of the Earth to be at x equals 1, sorry, at x equals something c squared over a, then
Yeah.
so then with this, if this point corresponds to tau equal to 0, it means that x at this point is what? Is c squared over a, right? But if we want xe to be, let's assume that let's choose the origin such that xe is equal to 0. Then well, I think by xe you mean something else. Let's choose the coordinates such that x equal to 0 at this point along this line. Then we have to translate this equation so that at tau equal to 0 we are at the origin, right? Do you agree if at tau equal to 0 this is not 0?
no.
We want it to be 0.
Okay, so we just like subtract it.
Yeah.
Yes.
From x.
From x. From x.
Not from the upper one.
What?
Yeah, the equation above.
From this?
Yes.
Okay, gosh.
Yeah.
Okay.
No, I see.
Okay, but I didn't see this. So we'll change them because I just use it like that and then try to eliminate tau by like x squared minus c d squared. But I didn't have this term. Because if we just do it like the way I had before, then you have just cosine square, hyperbolic square minus sine hyperbolic square. And you just can, at the end, you can just solve for t. And you get this. But I didn't have this term, and then change like the procedure that I followed.
Well, the only difference is that your x and this x are different by constant shift, so the result will not be too different from what you obtain. Whenever you have x, you should just replace it with x plus c squared over a, right?
Okay, yeah, because it's not. Yeah. Then so just going to do that and okay. So I would have to recalculate them because.
So can you write the correct equation?
Yeah.
And so t is equal to what? 1 over c times the square root of.
C squared or A, right?
Mm-hmm.
Square times C4 A squared.
Okay.
Yeah, and then just calculate out from by solving this.
Uh-huh.
Which was just like C over A sine f of everything versus A T C4.
Mm-hmm.
Should I write the numbers that I got, or although they are
Well, before getting to the numbers, I think there is one thing to be careful about, which is that what is the value of x that you want to plug in here?
it will be like 20 kiloparsecs because it's the total distance. So it will go and come, and they are asking us for that. Or I could just.
I mean, there will be. So let's consider. Let's on the same diagram. Imagine that instead of pushing the brake, instead of decelerating, imagine it continued. The spaceship continued moving forward.
Okay.
So can we just draw the same diagram?
If it doesn't break.
Yeah. So
it keep going like this.
Yeah. So it keeps going, right? So imagine I try to calculate now. Just on this diagram, when would you guess it arrives at 20 kiloparsec?
It will arrives at 20.
Yes. So
like this.
yes. If I kept accelerating, when would I arrive at 20 kiloparsec? Roughly. I don't want exact.
Yeah, it's like.
Basically, I want to see compare it to the turning, like the times at which it arrives to the center, and the times that it arrives back.
If it just keeps going, it's like square root of 20 divided by. It's like a kinematical.
No, just on this diagram, let's just mark 20 kiloparsec on this diagram, and let's have some rough trajectory for the astronaut who is constantly accelerating.
Something like that.
Yeah. So, do you still think that we should plug in 20 kiloparsec to get the total time?
No, it will be like.
We'll be underestimating the time, right? And the reason is that at some point it starts decelerating, so it moves slower. But if it kept accelerating, it keeps moving faster and faster.
Okay. So yeah, then that will have to like just like split the motion here and calculate this time and this time, and then I could just multiply it by 2 because it would be the same time here.
Right. And
the summation.
Right, but there is also. Do you also see some relation between the first half of the trip, the accelerating part, and the decelerating part of the trip?
It would be the same. Or
yeah, it's like almost like the mirror image, or the.
Yeah, so I could just calculate 5 kiloparsecs then, and then just multiply it by 4.
Okay. But yeah, I guess the number would be different.
Yeah.
So, what do I get? I think I'm getting 30 years for the onboard clock and 10 to the 5 years for the Earth clock.
I got around 40,
Okay.
41.
Right. Probably square because I wasn't too careful with the number. What about the Earth?
It was 10 to the power 5 or something. Yeah.
10 to the power of 5.
4, yeah, 10 to the power 4.
Okay.
65.
Okay, thank you.
10 to the 4.
So someone is for part B. 9. Jorge, can you do part B?
Yeah, yes, I will try. No, I think I.
Okay. No?
Okay. So what I did was use conservation of momentum. I mean,
Sorry, can you read the question?
yes. What is
Just
the
part B?
initial mass of the fuel is m. So calculate the initial mass of the fuel.
Okay.
So what I did was, okay. So because with this, I mean, what is making like the force is the changing in the form momentum, which is at the end is the force. So what I did was first I have the initial or the total. I mean, first I have before any before using any fuel, I have my rocket, which is going to be the mass of the rocket plus the passengers plus the fuel, and then this is almost like I thought that this is like decaying. So after we convert some mass of the fuel into photons, this would be like emitting a photon plus the rocket. So it's almost like a decay problem, which are different mass. Let's say m prime, and this is carrying some energy. So initially our form momentum. Okay, so additionally we have this. Let's say the form momentum, which is at rest at the beginning. Let's say constant. So we have. I'm going to just call it m. And then I'm going to have this. Okay, there is a thing that this is seen in the center of mass system, which is not the same as the laboratory system. So I'm going to make a plot. So it's like I have my observer here, I have the rocket here, and the rocket. I mean, the observer is going to not is not going to see the I mean, because these are photons. How to say? Are you going to see this velocity and this velocity of the? Let's say this is u. This is the velocity c of the
Photon.
of the photon. But I want to compute c in this rest frame. So what I need to do is to take the difference. I don't know how to plot it.
Sorry, can you explain what you are trying to do?
What I want to do is something like this. So the force is going to be the change on this for momentum, which is going to be mass and the. So this is the initial for momentum. So the change is going to be the force, and this force is going to be due to the emission of this photon. I'm going to make this. I'm going to first start like thinking that this is not a photon. This is something with mass. and then we are going to make the change to the photon case. So this is going to, so the change in the total momentum is going to be a little emission of mass dm times the times it's for momentum. So yes.
Can you write the four momenta of those that photon and the spaceship after? So you had the initial four momentum, which was m and 0. Can you just write down the four momenta for the photon?
In the center, okay.
In the same frame. So I had a frame at which this spaceship was at rest. Then it emits a photon. In the same frame, we want to write the four momenta of the photon and the spaceship.
So let's say this the photon, and the spacecraft is just going to be let's say I prime like this.
But we can parameterize it in terms of, say, so you said its rest mass is m prime. It will probably also have some velocity, right? So when it emits a photon, there will be a kick. So it's gonna move with some velocity. Let's call it v. So if I know the rest mass and velocity, I know what is p mu, right? So what is the four momentum of an object whose rest mass is m prime and whose velocity is v?
It would be m prime b squared plus m prime, and then this part is going to be m prime. I mean with gamma. Yes.
No, I don't understand. The m prime squared plus m prime.
Because this is the energy, and this is the momentum.
Well, this is, I have problems with dimensions now, because
sorry. In this moment.
So you have gamma m prime v squared plus m prime squared. And where does that come from?
You say that this thing is moving with a velocity v after the kick. So after the kick, it has. I mean, I'm using the relation e squared equal to this. So after the kick, it has some velocity, which is v, and the momentum is gamma m prime v, and the energy should be this.
Okay. Yeah, I guess it has a simpler, more familiar expression, but I think if you open it up, it should be the same thing. I remember what is for velocity is because gamma times 1 and v, right? So there was, and then the for momentum was just m times for velocity. So if I mean,
Yes.
it's correct, but it looks a bit intimidating.
Sorry. I mean, yes, I think I can just put gamma m
M prime.
m prime.
Okay.
Okay.
So now we can use conservation of energy and momentum, right, to relate the to find a relation between E and V and M prime, right?
Yes. So initially,
We can also make another assumption. Imagine the photon has very little energy, so that the kick is very small.
infinitesimal.
Therefore, V will be tiny.
dV.
If V is tiny, then we are in the non-relativistic limit, right? We can just linearize in V. So then gamma would be what?
Gamma would be 1 plus 1 over 2 P B.
Well, what is the exact expression for gamma?
B squared, sorry. 1 over 2 B squared. Yes.
But if we linearize in V,
So it's just 1.
okay.
Okay.
Yes, but it is a familiar expression. It's just the rest mass. The energy is the rest mass, and the momentum is the usual non-relativistic momentum M prime. So let's write P mu for a very small V.
Okay. It will be M prime. 0.
No.
Well, let's linearize in V.
I would say M prime B.
Yes.
Okay, yeah.
Okay.
Now we can try to use the energy momentum conservation to relate E, M prime, and V, right? To the original mass.
E M prime and B. E M prime. Okay. Okay. So initially it would be the initial mass equal to the energy of the photon plus the final mass and the conservation of the momentum will give me 0 equal to, just M prime B equal to E.
Okay.
Yes.
So then if we eliminate E,
Which is this. Yes. And then.
so let's remember what is the goal. We want to understand, we want to find a relation between the change of the mass or the rate by which we lose mass to the acceleration, right? That's the goal. So the rate by which, so imagine this process happening in some time interval delta t or delta tau.
So I should. So the change of the initial mass would be in this time. Would be me.
Well, I would say that V itself is our infinitesimal, right? Because we were at rest and we considered some infinitesimal amount of mass to be emitted.
So you said.
We're not quite, but so let's do the following. Let me look at this one. This is okay, so what do we say? We say that I start from mass m, and then that mass m minus m prime is equal to the kick that we get. The change in the mass is equal to the kick that we gave to the spaceship, right? Moreover, since this v is already small, and we are doing to first order in v, then m prime is the same as m, right? The difference between m prime and m is infinitesimal itself. So this is mv. So now if this process happens in a time interval delta t, and this is what? This is minus delta m, right? Because this is m final, this is m initial minus m final, so this is minus delta m, so I can divide both sides by delta t, and remember that this v is also v final minus v initial, which was 0. So what we get is that minus dm d tau is equal to m dv d tau. So this is some result that I obtained in the rest frame. So what it tells me is that F in the rest frame, or the force in the rest frame, that we just call it a Newtonian force, that is equal to minus dm d tau. Okay, but this is a scalar quantity. So if you remember the norm, the for acceleration, or right, the norm of the for acceleration is a scalar quantity, and that is given by F Newtonian square. So that object is also the same as dm d tau square. So now that we have the for acceleration, we can okay. So now we want to ask what is the next step? We want to determine what this dm d tau, right?
Compute them in function of tau.
Sorry, say it again.
Compute them in function of.
Right. So now what the information that we have is that we have constant for acceleration. Right, constant
Acceleration.
proper acceleration. So what was proper acceleration? The proper acceleration was just the
rest.
Right, it was just acceleration in the rest frame, which means that I should just divide this F Newtonian. So a rest frame is just F Newtonian divided by the mass, which is therefore minus 1 over m dm d tau. So what we know is that this is a constant. This is basically what we call the proper acceleration. And it's basically 10. This is what the question gives us. So we have 10 meters per second squared, and now we have related that to the rate of the change of the mass in the rest frame. Now the only thing that we need to do is to solve this differential equation given the total time of the trip, which we determined in the previous part. That gives us m as a function of tau.
Mm-hmm.
It's a very simple equation, right? Because I can easily integrate it. It gives, so I have dm over m. I can integrate that is equal to minus a tau.
That's it.
Right. Plus a constant, but I take care of it soon. So this is log m over m0 is equal to minus a tau. That's the constant goes in the m0. So I get m is equal to m0 e to the minus a tau.
Mm-hmm.
Now with the, if I take the whole, if I consider the whole trip, then the final mass is going to be just the mass of the spaceship, and the initial mass is going to be big M. So that should be e to, they are related by this exponential factor a, and tau is the total trip time.
Mm-hmm.
The initial mass would be big M plus small
Plus
m,
small
right?
m.
Because according to the problem, big M is the mass of the fuel.
Mm-hmm.
Oh, okay, yeah. I thought big M is the total mass, but it doesn't matter. I think the difference is
-1.
Yeah, there will be -1.
It would be e to the power something very big.
Right. Yeah.
Mm-hmm.
Okay.
I don't know.
Thank you.
I don't know. I didn't use this. I didn't come out with the approach linearizing the form momentum, but what I did was more or less. I think it's the same, like working out this, like working out having like the change in the momentum is going to be is due to the emission of the kick of the bottom.
Mm-hmm.
But I did I mean I did it like for a instead of bottom like with something with mass and then taking the approximation that the mass is 0 and but the speed is speed of light.
Uh-huh.
And I mean it gives me a lot of equations, but yeah, I got at the end yeah I got the same.
You got the same result for the final mass in terms of the initial one.
Actually I get like this T, but instead of C, like the velocity of the fuel. I mean, if it is not light, but it came out, it's another chemical or something.
Mm-hmm.
I got this, but then I make the approximation that this is yeah.
Uh-huh.
I got. But
So you were assuming that this is your the fuel is emitted with velocity W, right?
yeah, like instead of like the decay of something with light, decay of something with I mean another piece of matter.
Yeah.
But,
I mean, you can. That's a valid problem to solve.
And then it came out that it gave the same. I mean, when because at the end the this mass, how to say it, at the end you erase the mass in terms of the big mass and the velocity, and then everything. I mean, this mass doesn't matter. The only thing that matters is the speed that it was.
Okay, I guess we should move on now.
Oh, okay.
Thank you. very suspicious of this random number generator. Keeps giving the same number. A lot. Can we do next problem?
The neutral sigma baryon, sigma 0, with mass m sigma, they get into a lambda baryon alpha with mass ma and massless photon. Find the energy of the photon in the rest frame in which the sigma 0 is at rest. So we will work at the rest frame for sigma 0. So I will write the four momentum for sigma 0 at the rest frame for this particle, which is the mass of sigma 0 and 0. The process is, let me just do the process here. So this is 0 photon. And energy and direction. So what we will use the energy momentum conservation. So by squaring the equation, this one will give us 0 squared equals 0, which is the mass of the photon, plus the mass of eta squared plus 2 P alpha dot E eta. Now P alpha dot E eta will equal E photon E eta plus P eta E photon. Now
Sorry, can I ask?
Yes.
So which question are you trying to answer now?
Question 4.
No, I mean which of them? Like you want the
We want the energy of the photon in the rest frame for sigma 0.
sigma 0.
Yes.
Can we first answer the rest frame of photon in the rest frame of lambda, given that you already have it on the board, almost?
What?
Can we just use your formula?
Yes.
No, right. To say what is the energy of the photon in the rest frame of lambda? What is the definition of energy of a photon in the rest frame of an observer? Like suppose I have an observer with 4 velocity u mu.
Yes.
So, and there is a photon with 4 momentum p gamma mu.
Yes.
So then, we want to ask what is the energy of this photon in the rest frame of that observer. Is there some scalar quantity that gives us the energy of the photon in the rest frame of this observer? So for instance, we can think, how would U mu look like in the rest frame of this observer? So let's put some index for U, UA, U Alice. Yes, so suppose this is a four velocity of Alice. So if I go to the rest frame of Alice, how would U mu look like?
I really don't understand the question.
Oh, okay. So,
So,
suppose Alice moves with velocity v.
Yes. So this
So-
is Alice.
It moves with velocity v.
Yes.
So what is the four velocity of Alice in terms of v?
U A mu, you mean? Which is yes.
Now let's go to the rest frame of Alice. What is the definition of rest frame of Alice? It's the frame in which Alice is at rest.
So there's no V.
Okay, so what is U mu of Alice in her rest frame? And what is gamma?
The rest frame, it's 1.
Okay. So U mu is just 1 and 0
Yes.
in the rest. Now, in the rest frame of Alice, there will be some p gamma mu. The photon for momentum has there will be some p prime mu
Okay.
of the photon in that rest frame. So when we say the energy of the photon in that frame, we just need to look at the zeroth component
Yeah, it's
of p of gamma in that frame.
Is it like U mu dot P? Or sorry, and the rest frame for this one? So it's just like so P energy and 0. This is
Of lambda of gamma.
lambda.
No, sorry, what are you trying to?
No, it's this is wrong.
Well, I'm just saying that if let's imagine let's continue. Let's imagine we go to the rest frame of Alice,
Yes.
right? So now there is also a p gamma mu, but in this new frame. So let's call it p prime gamma mu.
Yes.
This is the four momentum of the photon in the rest frame of Alice.
Yes.
So let's ask, what is the frequency of photon as measured by Alice? What would it be? It would be just looking at zeroth component of it, this p gamma of mu.
Yes. It's
So let's say p gamma is some 4 vector. It has energy E prime and momentum E prime because it's a null vector, so it has to. And when we say frequency of the photon or energy of the photon in the rest frame of Alice, what we mean is exactly E prime.
E prime.
But there is a scalar quantity whose value is equal to E prime, and we can calculate it. Like in the rest frame, it's just, imagine I take the dot product
Between
of u mu
And
and p gamma. That is exactly going to be E prime.
Yes.
But this is a scalar quantity, right? This is a product of two
Two
four
vectors.
It wouldn't matter in which frame I calculate.
Yes, it is because it's a
So
scalar.
then you can erase rest frame from U.
Here.
Okay. So now can you write it in terms of the original quantity? So I have UA mu and P gamma mu. What would be the energy of the photon?
Yes.
In terms of UA mu and P gamma mu.
Ah, you mean here?
No, what I mean is that, so imagine now, again, going back to this question, I have an observer Alice with a 4-vector u mu, and there is a photon with 4 momentum gamma. Now imagine I ask, what is the energy of the photon in the rest frame of Alice? Can we just write an expression? It's just UA dot P gamma.
Which is E.
Yeah, we don't need to expand it. It will have some expression, but I mean,
EV. Okay. It's the dot product between the 4 momentum with the photon with the velocity in the Alice frame. Right?
But there is also a gamma.
Yes, there's a gamma.
Okay. But okay, so let's keep it in mind that the 4-vector dot P gamma, that is exactly what we mean by energy of the photon in the rest frame of Alice. Now we want the energy of the photon in the rest frame of lambda. So lambda particle now is our Alice.
Just a second.
We just need to erase a little piece of Alice so that it becomes lambda.
Yes. So it's yeah, it's what is it? What is it?
Okay.
So we just plug this in here.
Yes, it's done.
Over to the mass of this is the energy of the photon at the first frame for the sigma.
Well, no. The energy in the rest
for
frame
lambda,
of lambda.
Yes. And the energy, the same question, but with the different first frame for sigma now. So it's just the same calculation, we're just changing the mass in here from from alpha to sigma 0.
Yeah, so that one can be done by doing doing basically the same calculation, but instead of squaring this quantity. So why did this equation become so simple? It's because this object was exactly related to the energy of gamma in the rest frame of lambda. So if you are interested in energy of gamma in the rest frame of sigma, it would be nicer to take this.
Yeah, we just change this equation to be the lambda equals b minus b gamma, and then squared. Yes.
Okay. Thank you. Oh, by the way, are there questions about what we did so far? Thank you.
Can I do? Do you want me to do?
No. Thanks. We are done. Any questions so far? Also about last problem, if there is some.
Can you just define? Sorry, just the covariant. What do you mean by the covariant equation are covariant? Just the definition, not the solution. For question 5. Just why is it covariant? Yeah.
Oh, well, covariant means that I think I tried to give the definition in the notes. Covariant means that an equation is covariant if its form is the same in all inertial frames.
Yeah. Can you just like an example?
I can give you many examples.
Just one. Just one.
So for instance, phi equals a mu. A mu is a covariant equation because it relates a scalar to the inner product of two 4 vectors, which is a scalar. So if I apply a Lorentz transformation to this equation, phi is invariant on the Lorentz transformation, but a mu times a mu with one lower and one upper indices, that is also invariant on the Lorentz transformation. So this is an example of a covariant. And this is an example of non-covariant equations because it looks differently in a different coordinate system. So let's just write the covariant ones. Take this. There's phi equals T mu. There is T mu equals T mu. Mu equals minus T mu.
T mu equals A mu. And the last two.
Alright, so now here is the one that is a bit. So this one is also the case. Because if I do a Lorentz transformation, then I will get a lambda, determinant of lambda, if I write it in the matrix notation, lambda and then a lambda inverse. But then this is equal to determinant of t. Yes, it's determinant of t times determinant of lambda times determinant of lambda inverse. So this part is 1. And of course this part phi doesn't change. So this is okay. This one is the one that depends what kind of transformation we look at. If we look at transformations, we determine and equal to 1, like proper Lorentz transformations, then also this one is a covariant. But if we look at more general coordinate transformation, which change the determinant, then the volume factor, then this is not a covariant equation. So later on, when we consider coordinate transformation, for those this will not be covariant equation. Okay, what else? There is the determinant in terms of the Civita tensor. So what is the trick to find the normalization? Any suggestion?
Survey with the delta, conquer delta.
Mm-hmm. Determinant of A. And as suggested, so we want to determine C. We can take A mu nu to be the unit matrix. We know what is the determinant of the unit matrix is 1. If I take it to be delta mu nu, then determinant of A is equal to 1. Now I can apply this delta Kronecker on the left-hand side. So on the left-hand side, I get epsilon mu1 to mu d, epsilon mu1 to mu d equal to C. Now, what is the property of this epsilon tensor? It is a totally anti-symmetric object. So its components are either 1 or -1 or 0. It's 0 if there are repeated indices. Then for symmetric, for even permutations of 1 to d, it is positive 1. For odd permutations, it is negative 1. But since they are multiplied together, it's always it is a square. So it is 1 for all possible choices of these d indices out of 1 to d, which is d factor.
Okay, could you repeat that last part?
Yes. So first of all, this epsilon is 0 whenever I have repeated indices. So this mu1 to mu d have to be all different from one another. It means that they have to assume all values from 1 to d, but they can have different permutations. For every permutation, since it is multiplying another epsilon, you square it, so it becomes positive. So the left-hand side is just all possible permutations of 1 to d, which is d factor. Yes, so C is d factor.
Is there a minus? There should be a minus. Because, I don't know, in Weinberg, still, it confuses me a bit. But it says that numerically, the epsilon with upper indices has a negative sign, which does lower indices.
I think it depends on the number of negative.
Yes, because of the signature.
Yeah, for example, in Lorentz. Lorentzian.
Oh, okay.
Should be minus 1 to the power signature.
Yes. Yes. It's correct because, so let's look at one of them. So epsilon 0, 1, etc. D. And then this multiplies epsilon 0, 1 to D.
Okay.
Right, then we want to see what is epsilon 0, 1 to D in terms of the upper index one. And this is equal to eta 0, 0 times eta 1, 1 times eta dd times epsilon 0, 1 to D. So this object is nothing but the determinant of eta mu nu, which is minus 1. Because eta 0, 0, in our notation, in our signature, eta 0, 0, or eta mu nu is basically minus 1 and then 1 everywhere. So this product is minus 1, and then we get, therefore the whole thing is minus 1 times epsilon 0, 1 up to D square. So it is, so this is 1, but there is an over a minus 1. So yeah, it is, so the correct answer is
Minus
D factorial times the determinant of whatever metric that we have. Okay. Other questions? There is no other question, then see you.
Yeah, you're really halfway.
Yes, because I don't have Wi-Fi in the room. And I see the laptop, but no, he said he's not coming here.
When did you come?
1:45.
Adesso posso tirarti una il problema è che non si può però
Is it a different node that you're